Point 1. Critical values. Objective 1. Given a graph of a function, find intervals in which the derivative is greater than and or less than 0. Objective 2. Given a graph of a function, determine the relative maximum minimum points, absolute maximum minimum points, and the x and y intercepts. Objective 3. Given a function, find the critical values of a function and determine if they are relative or absolute maximum minimum points.
Objective 1. Given a graph of a function, find intervals in which the derivative is greater than or less than 0. Okay, and the concept here is, remember that the derivative of a function simply tells us the slope of the tangent line. If the slope of the tangent line is equal to 0 or undefined, we call it a critical value or a critical point. Okay, so if we'll look at our slopes starting here of any tangent line in here, we realize that the slope of the tangent line is going to be negative all the way till we get to this point right here where it flattens off. And then the slope is going to be positive of these tangent lines. And then it flattens off again at the top of this hill. And then as we go down, notice that our slopes of these tangent lines are going to be negative from there on down. Okay? Now, so that means that our derivative, f prime of x, is going to be decreasing, or is less than 0, be in the interval from negative 2.5 all the way until negative 1, union with, and it's decreasing from here, which is at 1, all the way till we get to, let's say, positive 2.5. So that is the interval in which it is less than 0, and the interval in which the derivative is greater than 0 is from negative 1 all the way till it gets up to here, which is at 1. And the derivative was equal to 0 at the top of this hill, which was at 1, at x equals 1, and x equals negative 1. Objective 2. Given the graph of a function, determine the relative maximum minimum points and the absolute maximum minimum points. Okay, if we're given this graph below, I see that there are 4 critical points. 2 in which the tangent line cannot be drawn. And so in these 2 points, the tangent would be undefined. And these 2 points, the u up and the u down shape here, these 2 tangent lines is where the slope would be equal to 0 or the derivative would be equal to 0. Okay, because we'd have a flat tangent line in these cases. So these are the 4 critical points. Looking at this point right here, we are dealing with a relative minimum, and that height would be negative 2, and that would be at x equals negative 1. And in this point right here, we would have a relative maximum equal to 4 at x equal 1. And then we would have absolute maximum, and that would be equal to, let's call it 5. And that would be at x equals negative 2.5. And then we'd have an absolute min here, and that would be equal to negative 5. And that would be at x equals positive 2.5. We also have 3 x-intercepts. We have an x-intercept here, so I have an x-intercepts, and that would be at x equals 2. We have one right in here, which would, let's call it x equals negative 1/2. And we would have an x-intercept here, that would be at x equals negative 2. And we would have one y-intercept, and the y-intercept would be at y equals 1. And that's got our critical values, and that's got our x and y intercepts. Objective 3. Given a function, find the critical values of a function and determine if they are relative or absolute maximum minimum points. Example 1. Find the intervals in which f of x is increasing or decreasing, and the relative extreme points of this function. And first, we remember that anytime you take the derivative of a function and it's equal to 0 or it's undefined, you have a critical value. So let's go ahead and find the derivative of this function. And using the power rule, we're going to get 12x to the third minus 36x squared. And let's go ahead and factor, because we're going to set it equal to 0. Because it's a polynomial, that means that it's going to be continuous all the way from the left to the right, so we don't have to worry about this function being undefined. However, let's see if and where it's equal to 0. So we're going to factor out a 12x squared. That would give us x minus 3 equal to 0. And then we'd separate them. So 12x squared is equal to 0, and x minus 3 is equal to 0. And that's going to give us x is equal to 0 here, and if we add 3 to both sides, that would give me x is equal to 3. So we've got 2 points where we need to look. Now let's go ahead and set us up a chart. And we're going to set up a chart, and we're going to put 0 here and 3 here. And this is going to give us 3 regions. 1, 2, and 3. Give us 3 regions. And what we're going to do is we're going to test points in these regions. So if I pick a point in here, like maybe -1 would be a good point, and I plug it into my function. Now I'm going to use the factored version of the function. So let's come over here. 12x squared and x minus 3. If I plug a -1 in here, -1 quantity squared would be +1. It's going to give me a positive value. Times, if I put a -1 in here, that's going to give me a negative value. And a positive times a negative is going to give you a negative. And so we know that our derivative in this area is going to be negative. All right. Let's try that again for a value in region 2. Let's pick maybe 1. Okay, if we do that again, if I put 1 in here, that's a positive value, times. If I put 1 in here, that's going to give me a negative value. And a positive times a negative gives me a negative. And so that's going to give me a negative value in region 2. And last, pick a value like 4. 4 would be a good number to represent region number 3. If I put 4 in here, that's a positive value. If I put 4 in here, that's a positive value. And so a positive times a positive will give me a positive net. And so this will be positive. So by looking at my region, we know that the derivative or the slope of the tangent line is negative from negative infinity all the way to 0, where it flattens off. Instead of increasing, it's going to continue to decrease all the way through region 2, and then it flattens off again at 3, and then it turns and goes positive. So basically, if we're looking at the function, it's kind of going to come down, flatten off, continue to go down, and then it's going to curve like that. Okay, and we know that the endpoints are going to be positive and positive, because if you'll remember from algebra, our leading coefficient is 3. The degree of the polynomial was 4. Leading coefficient was positive, which means the end behavior is up and up. This function is going to kind of give it this feel because it's up and up. So we're looking at a relative minimum point at 3. So we have a relative minimum point at 3. Since it goes up and up in both directions infinitely, we have no maximum point. At 3 is the only minimum point we have. It's also going to be an absolute minimum point. Okay, so we have it's a relative and an absolute minimum point at 3. Example 2. Find the intervals for which f of x is increasing or decreasing and the extreme points of the function given that f of x is equal to 36x over x squared plus 36. So in order to find our critical values or extreme points, we need to take the derivative of this function. And remember, we're going to have to use the top being u, the bottom being v, u prime v minus u v prime over v squared, because we're going to have to go ahead and use the quotient rule. So we're going to get f prime of x is going to be equal to the derivative of u, which is 36, times v, which is x squared plus 36, minus u, which is 36x, times the derivative of v, which would be 2x, all over x squared plus 36 quantity squared. Okay, so we've taken the derivative, and I'm going to take factor out a 36 out of the top to make this thing a little bit easier. So that's going to give us 36 block, and we've got x squared plus 36 minus, and if I take a 36, that's going to give me 2x squareds all over x squared plus 36 quantity squared. And then I can combine my like terms in the top there, in the numerator, which would give me 36 times negative x squared plus 36 over, and that will be x squared plus 36 quantity squared. And that is my derivative. Now we don't have to worry about the denominator being equal to 0, and therefore we don't have to worry about the derivative being undefined, because if we set this equal to 0, then you're going to end up with the square root of a negative number. So we're okay there. Now, where we do need to look for is where the derivative would be equal to 0, which means that the numerator would have to be equal to 0. So let's look at this point right here. We need to look at where negative x squared plus 36 will be equal to 0. Let's subtract 36 from both sides. So that's negative x squared is equal to negative 36. So that's when x squared is equal to 36, and then we take the square root of both sides. So x would be equal to plus or minus 6. So here are some critical values. So let's take a look at these, and let's find on our little chart. Here is negative 6, and here is positive 6. And that's going to give us 3 regions. And let's look at these 3 regions and determine if we have any changes in the derivative. Okay, now we know that the bottom is automatically equal to 0. So what we need to do is look at the top and find out what happens. So let's take a test point, and we're going to use that top part right there to determine whether this function, so we've got 36, which is automatically positive, times minus x squared plus 36. Okay, so if we put in a number like negative 7, would be a good number for us to put in. If we put in negative 7 quantity squared would give me 49, and so that would be a negative 49 plus 36, and that's going to give me a negative value. So my slope is going to be negative here. Let's say I put in 0 would be a good number in region number 2, and if I put that in this function, that would give me negative 0 squared, which would be 0 plus 36 on the inside of that if I put 0 in there. And that would give me a positive value. So notice my slope changed at negative 6. It went from negative to positive. So that's going to give us some kind of critical value. At 6, if we plug in, let's say plug in 7 here. So that would be negative quantity 7 squared plus the 36, which would be negative 49 plus 36, which will give me a negative value. So here we have another change. So if we look at where derivative is equal to 0, the derivative is less than 0 on the intervals of negative infinity all the way to negative 6 where it flattens off, and that would be union with from 6 to positive infinity. And the derivative of x would be greater than 0 from negative 6 to 6. If the derivative is less than 0 and then it changes and starts becoming, then we have a relative minimum point at negative 6. Since it's positive and then becomes negative in region 3, we have a relative maximum point at 6. In example 3, for the function below, find the open intervals in which the function is increasing and decreasing and the extreme points. First of all, we need to watch this function and make sure that we are looking at a domain that exists. Alright, so let's take x squared minus 121 and set it equal to 0. We can factor that and get x plus 11, x minus 11 equal to 0. And so we would have x is equal to plus or minus 11. Now what we need to do is take a little number line here, and we need to put in negative 11 and 11. And we need to check our domain out here. Alright, so let's see. If I put in negative 12 in there and we squared it, that would give me a positive 144 minus 121, which would give me a positive value, so we're okay there. Because we wouldn't be able to take the square root of a negative number. Alright, let's put 0 in here. If 0 squared minus 121, that will give me a negative value in here. And so if we have a negative value in there, we know that in between negative 11 and 11 that our domain does not exist. And if we put in 12, that's going to give us a positive value on the inside. And so we know that our domain consists of two areas. One from negative infinity all the way to negative 11, and that's including 11, union with 11 all the way to infinity. Okay, now that we've got our domain issue straightened out, let's go through and let's find out where f prime of x is. Let's take the derivative so that we can see if we can find some critical values. And I can rewrite this as x squared minus 121 to the 1/2 power, which would give us 1/2 times x squared minus 121 to the negative 1/2 power times the derivative of the inside, which would be 2x. Notice the 2's would cancel, which would give us x over, and since it's the negative 1/2 power, I would drop it and put it under square root. So it'd be x minus 121. Okay, we need to look at values in which either this derivative does not exist or where this value is equal to 0. Well, the only value that would make this equal to 0 is if I set the top equal to 0, and x equals 0 cannot be a critical value because remember, our domain only exists in this. So x equals 0 is out. So let's look at where this value, the denominator would be equal to 0, where the value would not exist. Okay, and so we would have x squared minus 121 would be equal to 0. It was the square root, but that's still going to be equal to 0. Okay, so we would add 121 to both sides, or we could have factored either way, so that gives me x squared is equal to 121, and we know this from earlier that x would be equal to plus or minus 11. So given this, we've got two possible critical values where the slope does not exist at positive and negative 11. So let's take a look at these. So again, I'm going to use my handy dandy number line, put in negative 11 and 11. Now we know that this is no good. This area is no good, but let's check the left area, region 1, and let's check region 3. These are the two areas that we need to look at because we know the middle doesn't have a domain there, so it's not any good. If, looking at the denominator, which is the square root of x squared minus 121, if I were to put a test point, negative 12, in here, negative 12 squared is a positive 144, and 144 minus 121 would give me a positive square root. So I'm going to end up with for region 1, I'm going to end up with a positive derivative. Okay, for region 3, if I put 12 in, the same thing is going to happen. So in region 3, if I put positive 12 in to my square root function, then I'm going to get a positive derivative. Since our derivative is x over the square root of x squared minus 121, let's try some test points. Negative 12 here would be a good test point. If I put negative 12 in, that would give me a negative on the top side. If I put negative 12 here on the bottom, that would give me 144 minus 121, which would give me a positive value. So I'd have a negative divided by a positive, which would give me a negative. So we know in region 1, our derivative f prime of x is less than 0, so it's negative. Okay, doing the same thing on the right-hand side, we've got x over the square root of x squared minus 121. If we plug in 12, we've got a positive on the top and 12 squared is 144 minus 121 will give me a positive on the bottom. And so here in region 3, we know that f prime of x, or the derivative, is greater than 0. So notice that as this function goes from negative infinity to negative 11, it is decreasing. So it is coming down until it gets to negative 11 and then it stops. Okay? And in region 3, the derivative is increasing. We've got a positive slope of the tangent line, and so we're dealing with a function that's doing something like that. Okay? And in this case, if you'll look at these 2 points, these are both relative minimum points. And actually, they're going to be the lowest points on the graph, and they're going to be the same. So both of these are going to be relative minimums and absolute minimums. So we have an absolute min at 11 and negative 11. So this is one of the neat cases where you have 2 low points and they happen to be the same value. Example 4, for the function below, find open intervals where the function is increasing, decreasing, and the extreme points. Okay, the first thing we need to do is we need to find out where the derivative is either equal to 0 or does not exist. So the first thing we're going to do is let's find f prime of x. Okay, and in order to take the derivative, the second part of this will go away. But the first part, we're going to have to use the product rule. Okay, where x, it will be x to the 12th power will be u, and e to the x will be v. So that will give us u, which is x to the 12th, times the derivative of e to the x, which is just e to the x, plus the derivative of the first one, which is 12x to the 11th, times the second one, which is e to the x. The domain of this function will exist everywhere. So now we need to look at where this function is going to be equal to 0. So we can factor out x to the 11th e to the x, and that would give me x plus 12. And then we could set each of these separately equal to 0. And we're going to get x equals 0 for this one. And for this one, if we subtracted 12 from both sides, we're going to get x is equal to negative 12 for this one. So here are our 2 values that we need to be concerned with. Now we're going to set up my little chart here. We're going to look at the values of 0 and negative 12. We're going to plug this into my functional value here. Okay, so let's start off. If we put negative 12 in, let's try a test point of negative 13 in here. If we put a negative 13 in the first part, that's going to give me a negative. And in the second part will also give me a negative, because negative 13 to the 11th power will have 11 negatives. And so that's going to give me a negative value. So I'll have a negative times a negative. And so that'll give me a positive derivative value in region 1. Okay? So there's region 1, region 2, and region 3. And so let's take the second one. If I plug a negative, let's say a negative 10 would be a good representative of region 2. If I put negative 10 in, negative 10 to the 11th power would give me a negative in the beginning, times a negative 11 in here would give me a positive. So a negative times a positive would give me a negative derivative in region 2. And in region 3, let's try the number, a test point would be 2. If I put 2 in for this part here, that would give me a positive. If I put 2 in here, it would give me a positive. And a positive times a positive would give me a positive derivative. And so we see that because the derivative goes from positive to negative here, we see that negative 12 is going to be a relative maximum point. So we have a relative max at negative 12. And notice that the derivative is negative, and it changes and goes positive at 0. So we have a relative minimum point at 0. To find the actual relative maximum point, what we're going to have to do is we're going to have to, since we know at x equals negative 12 we have a relative maximum point, then we're going to need to actually plug negative 12 into the function. So we know our x value is, so if x is equal to negative 12, then our function would be negative 12 to the 12th power, e to the negative 12th minus the 9. So we're going to plug that into the actual function value, and should give us a value of this if we plug that in our calculator. Now let's look at our min point. If we let x equal 0 like we said, and we plug that in, that would give us 0 to the 12th power times e to the 0 minus the 9. And so that would give us equal to negative 9. And so we would have 0.0 comma negative 9 would be the other value, and that would be the minimum. Example 5, for the function below, find the open intervals where the function is increasing, decreasing, and the extreme points. Now in this case we need to remember that we have a domain issue with the natural log of x. X shows that a domain in this function must be greater than 0, because we can't put 0 or negative numbers in for x in the natural log. So that restricts our domain. So when dealing with this function, we need to remember that. Okay, so let's go through and let's find f prime of x. So if we take the derivative of the first one, that'll be 16 minus 8. Let's take the derivative of the second one using the product rule, which is u v prime plus u prime v. So x is being my u and ln x will be my v. So u would be x times the derivative of the natural log, which is 1 over x, plus the derivative of x, which is 1, times the natural log of x. So that would be equal to 16 minus 8 times 1 plus the natural log of x, which would be 16 minus 8 minus 8 times the natural log of x. Put these two together, and that would give me 8 minus 8 times the natural log of x. And we need to set this equal to 0. So I'm going to subtract 8 from both sides. So we're looking at negative 8 times the natural log of x is equal to negative 8. Divide by negative 8 on both sides. And so that would give me the natural log of x is equal to 1. And remember that natural log is the same as log base e of x is equal to 1. And so using our definition of a log, e to the first power is equal to x, so x is equal to e. So on our number line, we're dealing with e, which is like 2.7 something. So we need to check and see what the derivative looks like on the left-hand side and the right-hand side of e, because we only have two regions, region 1 here and region 2 there. Since our derivative is 8 minus 8 times the natural log of x, then let's plug a number in, and we got to be careful. We can't put anything less than 0. It's e to 0 here. So we're looking at an area in here. Let's put in 1 and see what happens. So that would be 8 minus 8 times the natural log of 1. And the natural log of 1 would be equal to 0. So we'd have 8 minus 8 times 0, which is going to be 8. So we've got a positive derivative here. Let's put in a number that's larger than e. So let's try maybe 3. So that'd be 8 minus 8 times the natural log of 3. And if we look at this value, it's going to give us a negative value for this when we put this in our calculator. And so we would have a derivative that is negative in region 2. So if we look at this function, notice that the slope is positive, so the function is increasing all the way till it gets to point E. And then the slope turns negative, so it's heading down forever. Now remember, this starts at 0, because remember that this function must be greater than 0. And so what we're dealing with, not only a relative maximum, but also an absolute maximum, and that's at E. The derivative of this function is increasing from 0 all the way up to E, is where it's increasing, and it is decreasing from E to infinity, and it has an absolute maximum at E.